What's going on, everyone? Johnny Bannon here with Trepa Technologies. In today's video, we're starting our Domain 2 section now. So let's go. Now we're going to get into routing, switching, layer 1, and some Wi-Fi. So in this section, let's go ahead and look at the exam objectives real quick. Let me bring them up. It's all about routing technologies. So, man, I could talk about this for like hours. Let me get my face out of here. Routing technologies, right? So we could deep dive into really everything here. NAT, first hop redundancy protocols, all the dynamic routing protocols that it wants you to learn about. But we're not. We're going to high level overview. What is routing? What is static routing? What is dynamic routing? What are the routing protocols? How does a router choose its best path? And then we'll get into these other router technologies. I call them router because like NAT doesn't teach you how to route where the best destination is. It's just a technology that's at the router, so I think that's why they put it in here. First hop redundancy protocols. I've always configured those in distro switches personally in my campus networks, but it is part of a router or routing. And then we'll go over sub interfaces and virtual IPs, which virtual IPs are a part of first hop redundancy protocols, and sub interfaces are what we create on a router when doing inter-VLAN communication. So we're going to go over these different technologies. Now to start, now that we looked at our exam objectives, I'm going to hit the whiteboard and go over really what is routing. Let's define it first. Let's go over the life of a packet, an IP packet with a layer 2, layer 3 header. How does it get from end to end? Where does the role the router play in that? And then show you how routing protocols enable that end-to-end connectivity. Because anytime we can get off the slides into some whiteboards, I'm going to try to do it. Okay, so our objectives start with static routing, but first, let's go over the life of a packet. I'm going to bring up our whiteboard here, and let's jump right into it. Okay, so this is our network that we're going to be going over. I'm going to go over the life of a packet, and this is going to relate to our routing, okay? So I'm going to get my face out of here completely just so I have enough room here. And all right, let's get to it. So in our scenario here, we have this network on the left. So we have two VLANs. We have our router here that has two sub interfaces that are going to be doing the inter VLAN routing and be the default gateway for our two VLANs here. We have PC1 with its private IP address, subnet mask. It knows its default gateway and it has its MAC address. PC1, let's draw out, right? It's packet now. PC1 here. That is not what I needed. I need my pen. So PC1 here wants to talk to youtube.com. So behind the scenes, it does a DNS request and it figures out youtube.com's IP address, let's say is 8.8.4.2. I have no idea if that's the real IP address. We could have done an NS lookup if we wanted, but for another time. So PC1, if you want to go step by step after that DNS request, opens up the web browser, right? It's already done ARP, so it already in its ARP table knows how to build its Ethernet header. So it's going to build a layer 2 header. The source MAC address is going to be our MAC. The destination MAC address, because it already did address resolution protocol, where it did the layer 3 to layer 2 mapping, it said, hey, this is my default gateway, but I need its MAC address, so it does an ARP request. Which device has this IP address? Give me your MAC address. Okay, then it puts that in its ARP table, its ARP cache. And let's say gig00 here, its MAC address is BB. That's the MAC address. So then we say, okay, the destination MAC is BB. Obviously, I'm shortening this up. MAC addresses are 12 hexadecimal digits. And now it needs to build its layer 3 header. So here's what's going to happen. So its source IP and destination IP are technically never supposed to change. Now we know that private IPs here are not routable on the internet. So on our outside interface here, R1, the customer edge, our demarcation point, is getting a public IP from the ISP. So what's going to happen is R1 here is going to have two tables that we're going to learn about in this section. It's going to have one, a global routing table, and two, it's going to have a NAT table. Okay? And that NAT table is probably, we're going to be using PAT, is going to do a mapping that says, hey, this private IP, our source IP, 10.0.0.2, is going to get translated into 1.200. And if it's trying to reach youtube.com via port 80, let's say, so this is our source port, our destination port is port 443, right? 443. Our source ports, let's say, is going to be something ephemeral in the ephemeral range. Let's say 42912. We're going to create a table, a NAT table that says, hey, when youtube.com responds back to us and its destination port's 42912 and its destination IP is 1.200, we know that that is mapped to PC1 in here in our inside network. And then, of course, our destination IP address never changes. Okay, so this is our packet. The packet that PC1 is going to build. And guess what? We're going to have our data payload at the end, okay? Our payload. Which is going to be, let's just say, the 1500 bytes of maximum transmission unit. Okay, so here we go, guys. So, when this entire packet reaches R1, two things are going to happen. One, the router is going to reference its global routing table, okay? Now let me zoom out here. Okay, the router is going to reference its global routing table. And that routing table may look something like this. So I'm going to call this the RIB, the routing information base. And it's going to say, hey, do I know where this destination IP is? I just got a request from PC1. PC1 wants to reach 8.8.8.4.2. Do I know where that's at? Well, I'm going to reference my global routing table. We make our global routing table by either A, putting in static routes, or B, building it with our routing neighbors with dynamic routes like ERGRP, OSPF, RIP, and even BGP if we're trying to route for autonomous systems in an ISP. Now, in this little network, more than likely, we would just have a static route. So that static route would be something called a default route that would say, hey, for any packet coming into our routing information base, we have a default static route for all 4.2 billion IP addresses via either gig 0/1, or it could be the next top IP address of 1.2.0.1. Also possible, right, in this routing table, this static route, so let me redraw it here, is also going to have its administrative distance and the metric, and then the next hop, which is either going to be a physical interface or the next hop IP address. We'll do the physical interface. So this is really what it's going to look like here. So this right here is going to be our administrative distance we're going to learn. This number right here is going to be our metric. This is going to be our exit interface, or our next hop IP. And then this right here is going to be our prefix length. So that's the first step. Next is, since we're going private to public, we're going to build a NAT table. And in that NAT table, we're going to have like our inside IP, which is going to be like 10.0.0.2, okay? This is like a port. We're doing port address translations, where it's always going to be happening. That is tied to 42912. And we're translating this inside IP to our outside IP which is going to be 1.2.0.0. And I ran out of some space here. But we also need to, in our NAT table, we're also going to have that port number. So 42912. So now the router knows, hey, when I get a packet, because I'm sending this out to youtube.com, sending it out gig01, it goes to the ISP routes you all the way to youtube.com. youtube.com is going to receive that packet, and the only change is going to be the source IP is now going to be 1.2.0.1, but everything else is going to be the same, right? And when it responds, it's going to build its layer 3 and layer 4 packet, and its destination IP is going to be 1.2.0.0, and its destination port is going to be 42912. And when our router receives that, it's going to be like, oh, cool. I'm getting a response, I'm getting a packet inbound from gig01 destined to 42912. That means that packet, whoever that's talking to us, is trying to talk actually to my PC N10-002, because that's what my mapping is, right? That's our NAT table, or our port address translation table. Okay, so now, at the router, you see its two major jobs here. Route our packets and do our address, maintain our NAT table, right? Our address translation table. Now let's go into the technologies that make this happen. So I'm going to make a new whiteboard here, okay? Zoom in a little bit. So we have static routing. So static routing is administrative. That's where you manually say, hey, you need to route here. In that example of the life of our packet, we did a default route that says, that was a stub in a network essentially. So if you come back up here, that says, there's only one way R1 had to go out to the ISP. It was a customer edge router, right? Behind it was no other routing environments or domains. So we did a default route. But we might not always have that. We may have something like this. Well, we have R1. R1 has a LAN. Okay, and its LAN is 192.168.0.0/24. And R1 may be connected to R2. Let me just redraw this. And R2 has maybe the same thing. So I'm going to copy this. Paste this over here. And let's get rid of that extra line. And this is R2. So let's say R2, it has 192.168.1. And in between here, let's just say we have 172.16.0.00/24. So .1 over here, .2 over here. This is a serial interface, and this is a serial interface. So now, if we want to do static routing, R1, it wants to talk, or its users really, the users down here, want to talk to this network over here. And the users on R2 want to talk to these users over here. Well, to do that, we know that R1 is going to have a routing table that's going to determine whether or not these networks can talk to each other. So what we're going to do if we want to do static routing is at R1, we're going to say, hey, R1. This is from the network administrator perspective. Hey, R1, I need you, when you get a packet destined to 192.168.1.0/24, I need you to send that packet to this next hop IP address or send it out this interface here. So R1, we're going to do that. We're going to say, hey, and this is Cisco syntax. Don't get too wrapped up around it. This won't be on the exam. I don't think it's CompTIA, right? Making static routes is different in every vendor. We're going to say, hey, R1, we want you to route traffic to this network. And we're going to put the network ID here with the subnet mask. And you're going to go out serial 0/0. And R2, we're going to do the same thing. R2, we're going to say IP route to 192.168.00/24. And you're going to go out serial 00. the same exact thing, okay? And once we do that, we're going to give these routers the ability to talk to each other. Now, on R1's routing table, if this is all we have here in R1, here's how it's going to look. So it's going to have that static route. Okay, let me zoom out over here. It's going to have that static route. This is our routing information base or our global routing table. And it's that static route, and this is the code here that says it's the routing table has this because it's a static route. We know where this network is. Our administrative distance is 1. Our metric is 0. And we're going to go out 0, 0, 0. Then we're also going to have these local and connected routes that are going to have this. That's going to be what's local to us. Okay? And that's going to be out gig 0, 0 down here. So it's going to say also, hey, we also know where our local area network is. And that's going to be out gig 0/0. Now, why is this important? Okay. Because when R2 routes traffic over to R1 and the destination IP, so again, let's say it's layer 3 packet, the destination IP is 192.168.0.10. When R1 receives that, it's still going to look at that destination IP. It's going to reference its routing table and say, do I know where 192.168.0.10 is? Oh yeah, it's local. It's a part of me. It's hanging off my gig 00 interface. So that's what the R1 routing table is going to look like. R2, guess what? It's going to be the exact same, but what's going to be the only thing missing? Or different, I should say. The only thing that's going to be different is that it's not going to be 192.168.1. R2 is routing traffic towards 192.168.0, the distant local area network. And that is static routing, guys. That's all it is. It's manually. So we go into the router and manually configure this. So let's take a look at something here. Here's my EVE-NG topology here, okay? And I'm going to bring my face back into this so you can see how excited I am. This is our EVE-NG topology. So if I have VLAN 10 over here and I want to talk to VLAN 10 over here, I have to go into R1 and R2 and configure those static routes, okay? So let's do it. So I'm going to console in to R1 and R2, which I already am. And I am going to make this happen. So in R1, I'm going to hit enable, config T. Don't get wrapped around this, guys. This probably won't be on the exam. This is Cisco syntax, okay? And I'm going to type in IP route 172.16. What are we working with here? We got to get to VLAN 10 over there, .10.0. It's a /25. And we're going to go out. What's our exit interface? Gig 00. Okay? Gig 00. And then I'm going to have to come over here to R2 and do the same thing. But R2 is trying to get to the 192 network. So it's going to be IP route 192.168.10.0. It's a /25. Out gig 00. And now if we want to look at a routing table and on the actual syntax, look at this. So we can see here, there's our static route saying, hey, if my PC, so let's say PC1 over here, wants to talk to PC1, you can see the IP address here. Let me zoom in though. Hanging off R1, it's going to go out gig 00. So the way this really flows is if a packet comes inbound to R2 and the destination IP address is for 192.168.10.20, the router's going to look at that destination IP R2 and say, yeah, I know where to send that, out gig 00. And it's going to go ahead and do that, okay? Okay, so now let's test this out. So I've been telling you guys, hey, this is going to work now. Let me clear this off. So let's see if PC1 over here can ping. Now this PC1 is part of R2's VLAN 10 network. it's going to try to ping PC1. That's part of R1's VLAN 10 network. Let's try to ping. And there we go. Our static routes worked. Before I started this lab, I didn't have anything configured. I did a ping test to make sure it wasn't reachable, and it wasn't. So now with static routing, if you take a look at our network diagram, we have enabled VLAN 10 over here on R2, VLAN 10 over here on R1 to talk to each other. Now we didn't configure a static route for VLAN 20, 30, VLAN 20 and 30 on both sides. So you can see how cumbersome this could be. I'd have to create some more static routes to enable more connectivity between my subnets living in my local area network. This can be a pain. So what's our solution? Our next solution would be to create some sort of technology that dynamically shares the subnets with our neighbors. Imagine if we had something that says that R1 can shout to R2, say, hey R2, I got all these networks. You want to come over here? You want to talk to them? I got you. Come to me. Come to me if you want to talk to these subnets. And R2 can do it back to R1. And imagine they're speaking the same protocol to enable that. And they can dynamically now share with their neighbors' subnets. Well, that's what dynamic routing is. And that's what we're going to talk about now. So now we're at 21 minutes. Super long. Let's get into dynamic routing. And for this, we're going to touch on static routing on the PowerPoints, make sure we hit everything, and then move on to dynamic routing. Okay, so before we move on to dynamic routing, static routing. Simple form of routing where a network administrator manually configures a routing table. Cool, got it. Manual configuration, low overhead. You can see this stub network here. That's where static routing is perfect because, I mean, it doesn't matter. There's nothing behind this. We can only go out to our ISP, so a default route out is perfect. You can see other static routing scenarios. Floating static route, where we can use a static route as a backup for our dynamic route that's maybe using a faster link. And our example here, a T1 link is 1.544 megabits per second of speed. That's our floating backup static route. And our main primary route is going to be using OSPF, using fiber. We could also have a host route. So a host route is a static route that will route traffic to a singular host. So here in this environment, for all traffic, we use the primary. But when I want to specifically talk to server 2 over here, .3, I make a host route there that says, hey, but only when I talk from R1, when I get a packet destined to 172.16.03, use a secondary. So a host route. Okay, so now let's jump into dynamic routing. So dynamic routing is all going to have very similar characteristics. I start off going over BGP because that's going to be the one we don't dive into a lot. And that is because BGP is advanced. It's our internet routing protocol. We call this an exterior gateway protocol that routes between different autonomous systems. So when we have multiple ISPs, AT&T, Verizon, Spectrum, Metronet, Cox, which is from, I live in Arizona, or used to live in Arizona, that was our ISP. When the ISPs need to talk to each other and route traffic, they use BGP. So we have these BGP routers that route for the entire internet. And then within that ISP, there's going to be hundreds, a bunch of routers that are going to be routing traffic within the ISP, within that autonomous system, using an interior gateway protocol. So high level for the test, BGP is an exterior gateway protocol. It uses path vector, okay? So it uses path selection. So it uses attributes like autonomous system path and next hop to determine the best path. And again, this is routing between autonomous systems. Some key notes is that this is TCP based. So when we create a neighbor, a BGP neighbor, it's over TCP IP. So what we're saying here is that technically we can have this router. So let me bring my pen up. So we can have, like, let's say this is R1 here. We don't have a direct connection over here to, let's say this is R4, but we can create a BGP peering with them. Because as long as we have IP reachability, we create a TCP session with them, we can become BGP neighbors, okay? All right. So, whoa, that was a little quick there. So BGP, how does it come up? So the neighbor relationship. So eBGP neighbors, peers, are manually configured to establish a TCP connection. So because this is for the internet, this is not going to be as dynamic as what you're going to see when I configure EIGRP and OSPF. We configure BGP neighbors like statically pretty much. We type in remote AS, the remote autonomous system, and then neighbor, right? It's an actual whole command. So neighbor remote AS 26001. And that's how we configure BGP neighbors, okay? So you can kind of see the flow here. When we enable BGP on a router, it goes into an idle state. And then when we set a neighbor, right, we say connect. So that connect state is going to be the TCP connection, three-way handshake. Once we establish that TCP connection, so now we have IP reachability and we have an established session between the two routers that want to become BGP neighbors, we go into an open sent state where we're actually going to send, hey, let's become BGP neighbors. Both sides are going to do this. They're going to confirm that, yes, we can become neighbors. And then we're going to become established. And now we have BGP neighborship. And then we're going to send each other updates. Okay, now we're going to exchange the routing information. So the way that neighbor command, it's like neighbor, IP address, and then remote system. Okay. All right. Now let's get into IGPs. So let's come back to the whiteboard here. So we see our static routing here. We see that we had to manually input routes here. Okay. Now for dynamic routing protocols, let me up the font here. Let's say we have R1 here. We have R2 here. And R2 has its neighbors. And then R1 has some routing neighbors. And each routing neighbor has its own IP addresses, its own LANs. You have a LAN .0, and it's all /24s here. Then R2 has a LAN. I hope you see the point I'm trying to make here. /25. And then this is R4, this is R5, this is R6, and they all have LANs. (192.168.2.0), 192.168.3.0. Okay, so they have all their LANs. Now imagine trying to make static routes for all this. It's just too cumbersome. It just doesn't make sense. In this kind of routing domain, let's say this is an autonomous system. This is our routing domain. What we want to do for all these routers is enable dynamic routing. This is going to be something called an IGP, an interior gateway protocol. And we have a couple that we're going to talk about in the Network Plus exam. So we have EIGRP, we're going to go over. We have OSPF, we're going to go over. This isn't the exam objective, so I'm just going to put it here, RIP. So these dynamic routing protocols all attempt to accomplish the same thing. They're all going to send what's called hello packets out. So if I go and configure EIGRP on all these routers, on their WAN interfaces, so this is gig 00, this is gig 01, this is gig 00, 01, I missed 02, this is 03, right? Whatever the case may be, if I enable EIGRP and I say, hey, EIGRP, you're going to advertise these networks. So I go to each individual router and I configure EIGRP and I say, hey, share with your neighbors these subnets. Is this something you were going to manually configure? The router is then going to send hello packets out. Every router is going to send hello packets. And this is something that's, each routing protocol has their own unique way they're going to establish neighborship, but every routing protocol, IGP, is going to do the same thing. Send a hello packet. Parameters are going to have to match within the hello packets, and each protocol has its own parameters that need to match. Okay, we're going to dive into it. Okay, and once those hello packets are sent between our whole routing domain, next, so we established neighborship. That's step one. Next, we're going to send our topology updates. And every single routing protocol is going to do something different. OSPF is a link state routing protocol. It's link state. Okay? It's going to send link state advertisements, and it's going to have a designated router, a backup designated router, and a broadcast OSPF network that is going to take all those LSAs and then disseminate them to all the druther routers is what we call them, the ones that aren't the designated router, and it's going to build a link state database. ERGRP is what we call an advanced distance vector or hybrid distance vector, where it's going to be using the dual algorithm, and it's going to have something called K values that use bandwidth and delay, and that's also going to create a topology table. And we're going to have something called the feasibility condition in ERGRP, which selects the successor routes that will then be placed into the routing table. All right. I'm not mentioning RIP. I don't care. It's not really in the exam objectives. I just want you to know that's one of the first routing protocols. ERGRP, OSPF, hello packets, neighborship. They send their topology updates, whatever that looks like. OSPF is a link state. ERGRP is uses the dual algorithm, which is a hybrid distance vector, which uses K values to create a topology table that has successor and feasible successor routes. Okay. Then after the topology is exchanged, we're all synchronized. Okay, all of our topologies are synchronized between all of our routers using a routing protocol. We're going to place the best routes in our routing table. And this is done at the individual level. So whether we have a link state database that's fully synchronized, converged in OSPF, or we have an ERGRP topology table that's fully converged in all of our routers, now we start placing the best routes and putting them in our routing tables. And then once we've done that, we have a fully converged routing domain, and now our users can all have IP connectivity, and if we make a change, we dynamically update our entire routing domain within our routing protocols. And that's as deep as I'm going to go as far as an overview. That is how dynamic routing protocols work. Now, each routing protocol has its own unique things. For ERGRP, its hello packets. Whoa. Let me control Z. Hold on. Where'd I go? There we go. Whoo! Almost had a heart attack there. So for ERGRP, in its hello packets, when the hello packets are sent between routers, the autonomous system number we configure has to match. Our K values also have to match. When we make our topology table, when we start sending routing updates, where our topology table creates what's called successor and feasible successor routes. And we select these routes using the dual algorithm, which again uses those K values. And then we build our routing table based off the successor routes. So successor routes get put in the routing table. OSPF, it has a hello packet as well that gets sent out. And just a little side note, these hello packets have a multicast, dedicated multicast destination IP. And what has to match here is the MTU, the hello/hold timers, and also the area ID. There's also an optional thing called authentication for ERGRP and OSPF that have to match in the hello packets, but anyways. During the hello stage, when they create neighborship in OSPF, the default broadcast network, you would like the designated and backup designated router. Then all those, the designated router is going to get all the LSAs. So once we create neighborship in OSPF, we have to build a topology table, which is called a link state database. That topology table is built by getting LSA updates and the designated router creating a link state database that then gets disseminated to all the other routers in the OSPF routing domain, and their link state databases are the exact same, and they're fully converged. And then for OSPF, we run the shortest path first algorithm that uses bandwidth as its metric to place the best routes in the routing table. Best routes. So once our link state databases are fully converged with every single router in our routing domain, we run the shortest path first algorithm. Using bandwidth as the metric, we put the best routes in the routing table. That is dynamic routing. Our slides will dive deeper into it. Now, you may be asking, which is better? Why would I use the ERGRP over OSPF and so on and so forth? Before we get into that, we're going to get into how a routing table selects the best path in a multi-router routing protocol environment. So let's check this out. I'm going to pause the video, draw up a diagram, and go over this. Okay, so I have this diagram up on the screen now. I just paused and made this. So let's break this down a little bit. So we just went over dynamic routing at a very high level, the difference between ARGRP, OSPF, and the why behind it, why we need it. Well, now let's go over our best path selection, because it's not always going to be a clean environment where we say, hey, we have ARGRP for everything, so best metric wins. No, we may have an environment that we have here. So what I have drawn up here is R1. R1 has 4 routing neighbors. Each neighbor is connected with a different routing protocol. Okay? And each router connected to R1 is advertising the 1110 network with a different subnet mask or prefix. Okay? Prefix length. So R1's going to get 4 routing updates, each from a neighbor via a different routing protocol. And it's going to input those into it's going to decide which one's going to go into the routing table. Here's how it decides. The best path selection is determined in this order. The first thing that the router looks at to determine the best path is the longest prefix match. I'm going to touch on this first, okay? Regardless of what routing protocol it learned it from, regardless of the administrative distance, which equals the trustworthiness of a route, all that does not matter if there is a longer prefix. So let's touch on this. So let's say PC1 wants to talk to 1.1.1.10. So PC1 sends that to R1. PC1's hanging off R1's LAN, okay? R1's going to look at that destination IP 1.1.1.10. Now, if we come over here and look at this routing table, all 4 of these routes 1.1.10 can be a part of, right? 1.1.10 fits in all 4 of these. But out of these 4 routes that R1 learned about from its 4 routing neighbors, which one has the longest prefix? Right here. The longest prefix essentially means which route has the longer subnet mask, has the larger CIDR. You can look at this as which route has the most network bits attached to its subnet mask. So you may be looking at me like, okay, easy enough. So even though 1.1.1.10 can live in any of these networks, R1's going to send it to this neighbor, which is our RIP neighbor, has an administrative distance of 120, out gig 00. Easy enough. Now, sometimes when people learn routing, they learn that the lowest administrative distance is best. But guess what? In this scenario, that wasn't true. RIP has the highest administrative distance out of all of our routing protocols here. Don't worry, external ARGP, I just put that there because I like to give the most knowledge, but you don't have to worry about that in Network Plus exam. RIP has the highest administrative distance, but we still chose it. We chose it over ARGP, our static route, which has the lowest administrative distance, because before we care about administrative distance, we look at the longest prefix match, okay? And guess what? The longest prefix here is that RIP learned route. Now let's switch it up. Let's say PC1 wants to talk to 1.1.1.50. Where is it headed? Well, let me clear some of this stuff up here. It has to look at its routes here. 1.1.50. Does it fall within this network? Yes, it does. Does it fall within this network? Yes, it does. Does it fall within this network? Yes, it does. And to show you this range, here's the ranges for each. This is .0 to .127 lives off our OSPF connected router. .0 to .63 lives off our static route connected router. But this RIP route, does .50 live within this network? No, it does not, because our RIP router only has 0 to .31 attached to it. So this is out of the equation. Now, out of these 3, which one has the longest prefix? The static route. So we're choosing the static route. Okay, let me clean this up and do one more example. Because when I first learned about routing, this is something that never made sense to me. I had to learn it the hard way. So now let's say PC1 wants to talk to .89. Does 89 fall into here? Well, yes, it does. Does 89 fall into here? Yes, it does. Does 89 fall into a static or a rip route? No, it does not. So these two routes are not capable of sending to .89. .89 does not live within these two networks that we learned about from this neighbor or this neighbor. But .89 does live in these neighbors. But which one has a longer prefix? Our OSPF. So even though our OSPF neighbor has the higher administrative distance, it has a longer prefix. Awesome. So that is very easy to understand. Now, let me erase some things here. Okay. Let's erase some things here. So now let's say I edited this. So let me get in here. And I said every single one of these routes is ERGRP. Okay? And now we had these different metrics associated with them. Okay? So it's all ERGRP. So the administrative, actually, scratch that. Now let's say we have some OSPF learned ones and some ERGRP learned ones. And let's say they're all /24s. Okay, so if we clean this up just a little bit, they're all /24s. Some are OSPF, some are ERGRP. Okay, so this is ERGRP. This is OSPF. And this is OSPF. Okay, and they're all /24s. Well, now, guess what? Every single prefix length is the same. So now we look at 11.89. Where are we sending it? Well, we go into our next rule here. If the prefix lengths are all the same, the lowest administrative distance is going to win. Okay? The lowest administrative distance is going to win. So here, OSPF, the administrative distance is higher. Now between these two, we're going out gig 01 because that has the lowest metric, okay? The lowest metric. So when the administrative distances are equal, now we move in to the lowest cost or metric. And that's how we do our best path selection. And that should cover all of our routing. So I'm going to pause the video again and get back to our slides and let's go over the slides. Okay, so let's hit these dynamic routing protocols. So ERGRP, it's called the Enhanced Interior Gateway Protocol. It's Cisco proprietary. It uses an algorithm called Dual, the diffusing update algorithm. And ERGRP creates a loop-free path to the destination networks based on the best metric. So ERGRP enabled routers initially send hello packets. Okay, those hello packets, the autonomous system, the K values have to match. And if they do, ERGRP enabled routers will become neighbors. Once neighborship is formed, ERGRP is going to send hello packets at intervals of 10 seconds and a hold timer at 40 seconds. If we don't hear from our neighbor within 40 seconds, we consider them down. And that's how we maintain our neighbor table. Once our neighbor table is formed and maintained, we build our topology table. So ERGRP will build a topology table from its ERGRP neighbors using what's called update packets. We'll send update packets, and in those update packets are going to be the networks that we want to tell our neighbor about. OSPF. So OSPF-enabled interfaces will begin to send OSPF hello packets to its neighbors. I configure OSPF. It's a link state routing protocol. So any link that I want to route for is going to send OSPF hello packets. In those OSPF hello packets are hello and hold timers, the area ID, and the maximum transmission unit of that interface that's sending the hello packets all have to match with their neighbors. Once our neighbors come up and we form OSPF neighbors, we're going to start flooding the topology with LSAs. All the LSAs are going to get flooded to the designated router. That designated router will build a link state database and then disseminate that link state database to all the other non-designated routers in the OSPF topology. We'll execute the SPF algorithm, choose the best paths, and put those paths into the global routing table. The OSPF algorithm uses reference bandwidth. So we determine the best cost in OSPF by using a reference bandwidth divided by the actual bandwidth. Okay, route selection. So again, we talked about route selection that, at first we do prefix length, and then we do administrative distance, and then we do cost. So with this route selection, our prefix length, right? I kind of already went over that. So this is just another little demonstration here that if we're trying to get to dot 20, which path are we going to take? We're going to use the RIP route and go out gig 03, right? Because that is the longest prefix length inclusive of our destination IP. Administrative distance. So here's our administrative distance values. If prefix length is all the same, we go off the lowest administrative distance. Here's our ADs for all of our routing protocols. You may want to memorize these, so pause the video. If all the administrative distances are the same, we're going to go off the lowest cost. So if we're learning routes via OSPF and we learn the same route from 4 different OSPF routers, whichever route has the lowest cost attached to it or lowest metric, we'll select that to go into our global routing table. All right, I'm going to take a pause here because our video is way too long, and I'll go over NAT and first hop redundancy protocols in a part 2 video, okay? And then that part 2 video will have our quiz for all of this. When I made these slides, I did not think that it was going to take this long to get through everything. Also, on our learning management system, there's going to be bonus videos configuring your GRP, OSPF, and BGP. So if you're interested in that, please look at the description below. I'll see you in part 2. Do not forget to like, subscribe, and ring that bell, hit that bell, and share with your friends.